Lewis structures, non-equivalent resonance structures plus examples. Okay, so before we can talk about what non-equivalent resonance structures are, let's go ahead and talk about what regular plain old resonance structures are. So how do we get those? Well, they result when it's possible to draw valid Lewis structures where the octet rule is followed, but the placement of the electrons in the structure is different, i.e. maybe you have single versus double bonds, you might have single versus triple, you might have double versus triple, you would have different numbers of lone pairs on different atoms in the molecule. So all of them are valid Lewis structures, but the placements of the electrons are different. And resonance forms can be two different types. One is non-equivalent, which means they're not equivalent to each other. So if you draw two, they're not equivalent, and they can also be equivalent. And so we're going to look at both types of resonance forms. Basically, non-equivalent resonance forms can be distinguished from each other because one or more of the atoms have different formal charges in each of the structures. So when you compare two resonance forms to each other, the formal charge on the individual atoms in that structure is not the same. So these are the ones that we're going to talk about first. Okay, so resonance structures do help us describe the real bonding picture in the molecule. And basically, one structure often doesn't describe the real bonding picture or what's really going on bond-wise in that molecule. And equivalent resonance structures, if you have, like, let's say we have two equivalent resonance structures that can be drawn for a molecule, those would contribute equally to the overall bonding in that molecule, where non-equivalent resonance forms do not contribute equally. So basically, the contribution, or how much that non-equivalent resonance form contributes to the real picture, is going to depend on its distribution of formal charge in the molecule. And so we're going to find out how to determine which distribution of formal charge in the molecule leads to the overall most stable picture. And that's the one that's going to contribute most to the overall bonding. And generally, we call that the preferred Lewis structure. So the one that has formal charges minimized and is closest to the real bonding picture in the molecule. So let's talk about an example of non-equivalent resonance structures. We're going to learn how to distinguish equivalent from non-equivalent resonance forms. And so we're going to look at the azide ion. Okay, that's N3 minus. Okay, so we can draw three different valid Lewis structures. Now what you should do is attempt to do this yourself. So even though I'm going to give them to you and show them to you, you should make sure that you can draw three different valid Lewis structures for azide without looking. Now, note in these three structures that we've drawn down here, note that all I've done is move electrons around. I have not moved the atoms. Okay? And so that's going to be true for all of the resonance forms that we draw, that we are not allowed to move atoms. We're only allowed to move electrons. Okay, so now also notice, and this is really important, notice that if you add up all the formal charges on this structure, like -2 plus 1 is going to give overall -1, and notice that's the overall charge on the ion. That needs to always be true for a valid resonance form. Okay, so here's one. All right, so we have triple bonded, lone pair on one nitrogen, single bond, 3 lone pairs. Okay, you can see the formal charge. That's another thing you should make sure you can do. Calculate formal charge for each one of those nitrogen atoms. Okay, the middle structure, structure B, has 2 double bonded nitrogens, each of them with a -1 formal charge on these outer nitrogens. Inner nitrogen has a +1 formal charge. And same here, we have triple bonded nitrogen with 1 lone pair on this side, and then nitrogen with 3 lone pairs on the other. And again, the middle nitrogen has a formal charge of +1. So which of these are equivalent and which are non-equivalent to each other? So we're going to compare them to each other. Okay, so how can we figure that out? So what we want to do is analyze the formal charge on each atom in the molecule and the bonding. Okay, So notice, this guy has a nitrogen with -2 and a nitrogen with +1. Okay? Also has a triple bonded nitrogen and a lone pair. Now notice, we just have the mirror image over here with structure C. Okay? So those two resonance forms are equivalent. The formal charges are the same, the bonding pattern is the same. Okay? And in the real bonding picture, these two would contribute equally. Okay? Now this guy, he's clearly different, right? So you look at that structure, structure B, has two nitrogens with -1 formal charge and one with +1 formal charge. Okay? So that's how we can distinguish equivalent structures A and C from non-equivalent structure B. Okay? And basically this slide just summarizes what I just talked about. So A and C are equivalent and structure B is non-equivalent. Okay, so the bonding in the azide ion is actually a superposition or an average or a composite. Those are different words you can use for this of all of the resonance forms. But which one contributes the most? And that's how we're going to decide on the preferred versus non-preferred resonance form. Whichever one contributes the most, we're going to call it the preferred Lewis structure. Okay, now we're going to talk about this molecule again at the end, but right now let's just compare the three different structures and compare it to this experimental evidence. And that is that the azide ion contains two nitrogen-nitrogen bonds of equal length. Now what do we know about bond lengths for triple bonds, double bonds, and single bonds? So single bonds are longest, triple bonds are shortest, double bonds are in the middle, okay? And so from that information, we can actually figure out, even without using formal charges, that structure B contributes most to the real bonding picture. But we're also going to learn how to analyze the formal charge distribution to decide which structure is best. Now again, stay tuned because this will be at the end of the presentation. We'll come back to this guy. Okay, so let's do an example. So drawing non-equivalent Lewis structures for this molecule. We call this the fulminate ion. Has an overall charge of -1, and it's used in explosive detonators. Okay, so what we want to do is draw three Lewis structures for this molecule or this ion, and we're going to use formal charges to predict which is more stable, i.e. which is the most preferred structure. Now, just a note that the nitrogen is the central atom in this molecule. Okay, so here's our strategy. We are going to use the step-by-step procedure to draw three different plausible Lewis structures for this ion, the fulminate ion, okay? And we want to make sure that all of the structures follow the octet rule and they're valid Lewis structures. Now remember, you're only allowed to move electrons, not atoms. So you're not allowed to change the places between the carbon and the nitrogen and the oxygen. You have to keep them in the same order, okay? Now step 2, we're going to calculate the formal charge on each atom for each of the structures, okay? So that's our second step. And then finally, we're going to figure out which one is preferred or which one contributes most to the real bonding picture based on the formal charge on each atom and its electronegativity relative to the other atoms present. Okay, so we'll talk more about this also. Okay, so you should be able to draw three different Lewis structures, and I'm showing them all without formal charge right now, but those are the three possible Lewis structures that we could draw for this fulminate ion, okay? Now, which one of these guys is the best? How can we figure this out? That's what we're going to talk about. So let's go ahead and calculate the formal charge on each atom in each molecule, okay, in each one of these ions. Okay, so just a reminder, formal charges are calculated using the number of valence electrons minus the number of electrons assigned after division. So remember, we're going to mentally cut those bonds, and we're going to give one electron from each bond to each atom in the bond. So for structure 1, okay, so let's look at this guy. Then we're going to mentally cut this double bond and this double bond. And so we'll give 2 electrons to oxygen here. We'll give 2 electrons to carbon here, and nitrogen will get 2 electrons from this bond and 2 electrons from this bond. Okay? So it'll have 4. So you should be able to calculate these formal charges also. So it turns out that on structure 1, carbon is -2, so 4 valence electrons minus 6 in the division gives -2. Nitrogen has 5 valence electrons. We've given it 4 in the division, so that it comes out as +1. And oxygen has 2 lone pairs, 4 electrons plus 2 from here, so 6 valence electrons minus 6 electrons after division. So those are the formal charges for structure 1. So go ahead and calculate the formal charges for structure 2 and 3, and then we'll go through those answers. Okay, so for structure 2, did you get the right answer? So for carbon, comes out to -1, so 3 electrons from this triple bond plus 2 from the lone pair. Carbon has 4 valence electrons, -5 after assigning, so that's -1. Nitrogen comes out to +1 also, so 3 from the triple bond, 1 from the single bond, and it has 5 valence electrons minus 4 assigned after the division, so that's +1. And oxygen now has an extra, okay, so 6 electrons in the division from the lone pairs, 1 from the bond, that's 7. And oxygen has 6 valence electrons minus 7 electrons assigned after division, so it comes out to -1. So let's do the same thing for structure 3. Okay, so for this guy, now carbon has 3 lone pairs, and it gets 1 from dividing that single bond, so that's 7. Okay, so carbon has 4 valence electrons minus 7 assigned after division, so that comes out to -3. Nitrogen comes out to +1, the same as all of the others that we've done. And oxygen this time has 1 lone pair, has a triple bond, so it gets 3 from that triple bond. So oxygen is +1 in this structure. The formal charge is +1. Okay, so which one's best? All right, so here's just a summary of all the different formal charges. Okay, so again, make sure that you can assign formal charges easily for each one of these structures. Okay, so how do we decide which one is the preferred Lewis structure? So let's just go through these rules quickly. Okay, so 1, we want to obey the octet rule if possible. Now on all of these structures it's possible. Okay, but if possible we want to obey the octet rule. We want to minimize the formal charge, so this is the key. So minimize formal charge while preserving the octet. So we need to keep the octet rule. We need to obey that, surround each atom by 8 electrons, but we also want to minimize formal charge. And after we do that, we want to make sure that any positive formal charges go on the least electronegative atom, i.e. the most electropositive. So that's kind of the same thing, just saying it 2 different ways. Least electronegative would be most electropositive. And the negative formal charges, we want to put those on the most electronegative atoms as much as we possibly can. Okay, so overall, structure 2 is predicted to be more stable. So why? All right, so let's look at the formal charges for carbon and oxygen. Now notice, nitrogen doesn't change in any of these structures, so we can just ignore it. Okay, so let's look at structure 2. All right, so structure 2, we have a -1 formal charge on oxygen, which is favorable. We also have a -1 formal charge on carbon, which is not favorable. Okay, so let's look at the other 2 structures and just compare. Okay, now notice that we have a -2 formal charge on that carbon, so that's clearly less favorable than -1 on carbon, which is already not that favorable. Okay, and also notice that we have 0 formal charge on this oxygen, which is not as favorable as -1. Okay, so we can say that this structure is not as favorable as this one. Okay, as structure 2. All right, so now let's look at our final Lewis structure. So look at him. All right, so this is structure 3, -3 on carbon. Carbon is the least electronegative element in this molecule, so that is the last place we want to put -3. formal charge. And then also notice that we now have a positive formal charge on oxygen, which is also unfavorable. So that's how we get to the point where this structure 2 is the most stable. Another point to this is that anytime you have formal charges that are high magnitude wise, so 2, 3, whether it's +2, +3, -2, -3, that's always unfavorable also. And we try to minimize that as much as possible. Sometimes you're going to end up with that and you can't help it, but you always try to minimize that. So overall, this guy has the lowest magnitude formal charges, and the oxygen has a -1 formal charge. Carbon, we can't help it, has a -1 formal charge, which is why this is an explosive ion. Okay, so we've gone through all of those, so let's just summarize it a little bit more. Okay, so the second structure has maximum negative charge on oxygen, so the most we can possibly get. Okay, and it also has minimum negative charge on the lesser electronegative element. Okay, so -3, -2, and -1. So that's just another way of saying the same thing that we've already talked about. Okay, so here's our most preferred structure. So this is the structure that contributes most to the real bonding picture in the fulminate ion. All the formal charges have been minimized. The negative formal charge is placed on the most electronegative atom where possible. Of the 3 structures, the most preferred structure has maximum negative charge on oxygen, which is what we want. Okay, it also has the minimum negative charge on the lesser electronegative carbon atom. Okay, so -1 instead of -2 or -3. All right, so let's go back to azide. Okay, which resonance structure most closely describes the real bonding? Okay, so now that we know how to analyze formal charge, let's try it with azide. Okay, now all the atoms are the same, so we're going to have to think about this a little bit differently. Okay, still the same idea, but since we don't have atoms involved in the molecule with different electronegativities, we're going to have to think about magnitude of formal charge. Okay, so structure B has 3 atoms with non-zero formal charge. Okay, so 2 of the nitrogens have negative and the other one has a +1 formal charge. Okay, now notice on all 3 structures, nitrogen has +1, that central nitrogen has +1 formal charge. So we can pretty much just leave that out of our discussion. Now, on structure A and C, which earlier we said were equivalent, those each have 1 nitrogen with -2 and 1 with a 0 formal charge. So this magnitude of formal charge is actually unfavorable compared to just splitting it evenly and having -1 formal charge on each of those 2 nitrogens. So, like I say, all 3 have that central nitrogen atom with +1 formal charge, so we can leave that out of the picture. So we're going to just pick the structure that has minimized the magnitude of the formal charges. And having a negative charge on electronegative nitrogen is not unfavorable. Okay, so overall, structure B contributes the most to the real bonding picture. Okay, so just a few reminders. So you're not finished drawing a Lewis structure for a molecule until you've added all of the non-zero formal charges to the structure. So you need to put those on there. Okay, otherwise your structure is not done. When you're drawing the most preferred Lewis structure, formal charge must be minimized, and you also need to draw any equivalent resonance forms. So for instance, if you're the most preferred structure, or the structure that has the best distribution of formal charge, if that structure has equivalent resonance forms, you need to draw all of those, however many there are, in order to draw that overall structure for the molecule. And don't forget, the best way to learn to draw Lewis structures is to practice using these guidelines. So practice, practice, practice is the best way to learn to draw Lewis structures.